Here we're going to look at the electric field from multiple point charges. The magnitude of the electric field at a distance r away from a point charge q is given by the following equation. E is equal to kq over r squared. That is the magnitude of the electric field that is created or brought into being at a distance r away from a point charge q. Since k, which is a constant, is equal to 1 over 4 pi epsilon naught, for the record, has this value, 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. You might remember that K is 9 times 10 to the 9th approximately. So the value of epsilon naught is this right here. It's called the permittivity of free space. We could also write the electric field is equal to Q over 4 pi epsilon naught r squared. Those are the same. The top one is a little bit more convenient to use, but the bottom one is fine as well. Now, to find the electric field at a specific location when multiple point charges are involved, we have to use that equation for each of the charges and each of their respective distances away, and then we have to add up all of those contributions to get the total electric field. And we have to add these vectorially. So we need to take into account the direction. Let's try an example. So you can see in the picture on the left, we have some point P. There's no charge here. This is just a point in space. And it's a certain distance away from 4 different charges, which I've labeled 1, 2, 3, 4. And what we want to do on the right here, this is point P again. We've just blown it up over here so we can kind of see it. We want to draw the electric field vectors due to each of these 4 charges. And we want to label those vectors. So first off, we can see that charge 2 and charge 4 are the same magnitude, the same sign, the same distance. So do you see that those two right there are going to be equal and opposite to each other? And imagine putting a positive test charge here. There is nothing here, but we imagine putting a positive test charge here. And if we did, charge 2 would attract it. So there would be an attraction like that. Similarly, point 4, there's going to be an electric field directed that way, and it's equal. I've tried to draw those the same length. That's the electric field at point P due to charge 4. And then what about for these others? Well, charge 1 up here, this is a negative charge, and so there's going to be an attraction there. So let me draw that, say right there, and we'll label that the electric field at point P due to charge 1. And then what about charge 3? Remember, we imagine putting a positive test charge here, so this is going to be a repulsive force. And you can see that because the magnitude is 3q down here, and the magnitude up here is only 2q, this one's going to be a little bit of a bigger contribution, you see? Kind of like that. So the direction of this electric field is net in straight to the top of the page. So let's now derive an expression for the magnitude of this electric field. We can say that we don't need to worry about the contribution from 2 and 4 because they will cancel each other out. So what we're going to do is we're going to find the magnitude at point P due to charge number 1 is equal to, what's the equation? K times Q divided by R squared. KQ over R squared, where the Q here is, you can see I'm pointing 2Q, and the distance is 2D. That's the magnitude of the electric field contribution from charge 1. From charge 3, we use the same equation, K times Q, but here the Q is actually 3Q, as you can see. This is in the lower right corner of the video. And we want to divide by the distance R, which is 2b, and we want to square that. So what does this simplify to? This looks like 2/4, and this looks like 3/4. So 2/4 plus 3/4 is 5/4. So the net field has a magnitude of 5 kq over 4b squared. That's the magnitude of the field. And the direction of the field, as we showed there at the top of the screen, is towards the top of the page.